Welcome, this is Dr. Plague, and this video will be part 3 of making a flash memory programmer. So, let's recap what I did in the last 2 videos. In the first video, I worked on making and soldering up the hardware for the programmer. In part 2, I started writing the firmware for this programmer. I created 4 commands. A help command, which lists all the available commands and how to use them. A command that allows us to see what the current address is. A command that allows us to change the current address. And finally, a command to read the data from a flash chip at the current address. In this video, I will create an additional 4 commands. Plus, I will show another bonus command at the end of the video, so stay tuned for that. I want to be able to identify the flash chip so we know how large it is and whether I'm able to program it. I want to check if the flash chip is erased or whether there is any data in it. I want to be able to erase the flash chip. And finally, I want to add the most important task, the ability to program data into the flash chip. So, the next command I'm going to add is a command to ID the flash chip, and I'll use the letter I for that. And I'll create the identify flash function, along with its prototype in the header file. So now let's go to the flash chip's datasheet and look up how we can identify it. It says the product identification mode identifies the device as blah blah blah, and this mode may be accessed by software operations. Then it refers us to a flowchart in Figure 18. Let's go to that flowchart. You can see that there is a command sequence to enter the product identification mode. This command sequence has us loading data at certain addresses. In fact, if we look at Table 4, we can see all the available commands listed. These are standard commands used by most flash chips of this type, so we can ID more flash chips than just the 3 that I've shown in Part 1. So, if we look at the device operations section in the datasheet, it mentions that commands are written by asserting write enable low while keeping chip enable low. In our case, chip enable will be low the entire time, at least in my version of the firmware. So, the address is latched on the falling edge of write enable, and the data is latched on the rising edge of write enable. So let's make a low-level flash function that loads data into an address. I'll name this function WriteFlash and place its prototype into the header file. Now, don't confuse this function with programming bytes into the flash memory. I'll call that function WriteByte when I get to it, although I probably should have called it ProgramByte. Hindsight is always 20/20. So, in this function, I'm simply going to set the address and data lines to the correct values. Then I will set the write enable line low to latch the address, and finally set the write enable line back high to latch in the data. And that should be all we need to be able to send commands to the flash chip. So I'll go back to the identify flash function and get ready to enter the software ID entry command. Let's look back at the flowchart. First, we need to load AA into address 5555, so I'll do that. Then we need to load 55 into address 2AAA. And finally, we load 90 into address 5555. Now, we need to wait for a time period of TIDA. And if we scroll up, we can see that that time is 150 nanoseconds. But you know what? Some other flash chips may need more time for this, such as this here older Atmel flash chip. It requires 10 milliseconds. Therefore, I'll just use a delay of 10 milliseconds, so we can at least ID most other flash chips with the same pinout. And of course, I'll need to add the proper header files to use a delay. Now, if we go back to the flowchart, it says we can now read the software ID. How do we do that? If we look back at Table 4, the software ID entry has two notes, 4 and 5. Note 5 tells us that by keeping all address lines from A1 to the most significant address line low, we can read the manufacturer ID with A0 set to a low, and we can read the device ID with A0 set to a high. In other words, address 0 will contain the manufacturer ID, which is BF, and address 1 will contain the device ID, which is either B5, B6, or B7, depending on which chip we've inserted. Table 2 shows this same info, manufacturer's ID at address 0 and device ID at address 1. So I'll just read address 0 into the manufacturer ID. And address 1 into the device ID. Now I want to print out the ID codes that we read. And now we need to exit the software ID mode. You can see in the flowchart that there are two ways to do that. Not all flash chips will accept both, but most will accept the longer of the two sequences, such as this Atmel flash chip. It only lists the one sequence. So I'll use the longer of the two sequences. I'll first load AA into address 5555. Then 55 into address 2AAA. And finally F0 into address 5555. And we need to wait for TIDA before returning to normal operation. Again, I'll just use 10 milliseconds. Let's add this ID command to the help printout, then test it out. I'll compile and program this code into the Flash programmer. The command list prints out fine. The manufacturer's ID should be BF, and I'm using the SST39SF020A, which has a device ID of B6. Let's see if we can read that correctly. And this looks good. Let's use these ID codes to correctly initialize the Flash variable in the Flash programmer. Let's create an init Flash function to do this. And we'll place the prototype in the header file. So I'll use the switch statement to select the manufacturer ID. And I'll create a case for the SST/microchip flash chip that I'm using. There are 3 flavors for the device ID, so I'll use another switch statement for those. We have B5, B6, and B7. B5 is the 128K variety. B6 is 256K. and B7 is 512K. I'll set the correct flash size for each variety. And if it didn't find any, I'll just set the flash size to 0. Although I probably should have done this before the switch statements. Then I wouldn't need the default case. But this way, if no correct manufacturer's ID is found, then we'll still have the size set to the smallest expected flash size, which was initialized to 128K, so we might be able to program some unknown flash chips without modifying the code. Then, at the end, I'll just set the current address to 0. Okay, let's call this init flash function from the identify flash function and give this a quick test. By default, the flash size is 128K, so I'll set the address to the highest value within 128K, which is 1FFFF. I'll read a byte, and now the current address rolled over to 0. Next, I'll identify the flash chip, which should change the flash size to 256K. And I'll set the address to 1FFFF again to make sure it doesn't roll over to 0 this time. And it doesn't. It incremented to 20000. I'll set the address to the highest value for a 256K flash chip, which is 3FFFF. This time it should roll over to 0 after reading a byte. And it does. So that's working. Now, we'd like to be able to program the flash chip, but before we program it, we need to make sure it is erased. The datasheet says, before programming, the sector where the byte exists must be fully erased. Actually, that's not quite true. We can still write bytes to any location that is not already programmed. The entire sector does not need to be erased. If that was the case, then we would not be able to program more than one byte into any sector, because after we write the first byte, then the sector is not fully erased. So that doesn't quite make sense. Actually, we can also write a new value to a programmed address, as long as we do not try to set any bits from a 0 to a 1. For example, if an address holds the value of F0, we could program it to 00. But we can't program it to FF. I'll demonstrate this later on. Now, generally speaking, we normally want to erase the flash chip before trying to program it. It would also be nice to check whether or not the flash memory is already erased. So, let's create a command for that. And I'm not quite sure what to call this for a single character command, so I'll just use the letter Z. And I'll create the checkIfErased function along with its prototype. This will be easy. I'll just create a loop that goes through each flash address and reads the byte. And if it finds a byte that is not erased, I'll print out that data along with the address it resides at. And of course, break out of the loop in that case. I'll create a Boolean variable that indicates whether the flash is erased and initialize it to the erased state. And I need to include the standard bool header file to use the Boolean variable type. I'll change that variable to false if we find a byte that is not erased. Then, if the chip is erased, I'll print out a message to indicate that. Now, I suppose I could have skipped the Boolean variable and just returned from the function after printing the data and address, but I'll just keep it this way. Then I'll add the check if erased command to the help printout. Let's compile this. Oh, look at that. I forgot a semicolon. We'll fix that and recompile it. Then program it. The flash chip we're using is not erased, and if you remember from back when we read the bytes out of it, it had the value of 7F at address 0, so this should remain unchanged. There's 7F and BF at address 1. But the check if erased command will only look for the first programmed byte, 7F. And after checking if it is erased, it did find 7F at address 0. So that's working fine so far. So now let's go ahead and add a chip erase command. And I'll use the letter E for erase. Then I'll create an empty erase flash function along with its prototype. And let's look at the datasheet to determine how to erase the flash chip. And we can see from Table 4 that there is a chip erase command along with a sector erase command. So, remember back to when I created the flash IC structure? We could include info in there that indicates whether the flash chip supports sector erase, byte-by-byte programming, sector programming, etc. There's all kinds of info we could include. And if you want to add all this functionality to your programmer, then by all means, knock yourself out. But I'm just going to make this as simple as possible for now. So I'll skip any sector erases and just support a full chip erase. Figure 19 shows the chip erase command sequence, and we have quite a few bytes of data to load into a couple different addresses. AA goes into 5555, then 55 into 2AAA, eight zero into 5555, AA into that same address, 5555, five into 2AAA, and finally 10 into 5555. Now we're asked to wait for a period of TSCE, which is 100 milliseconds. Then I'll print a message indicating that the chip is now erased. And let's initialize the current address to 0. Let's add this to the help function. And let's give this a test. I'll make sure the chip is not erased, then I'll erase it. Let's check it again, and this time it comes back as erased. And we can see bytes being read as FF, which is the erased state. This is working great so far. Now for the command we've all been waiting for, or at least I've been waiting for this. This is probably one of the most important commands. Let's create a command to program a byte into the flash chip. I'll use the letter W to indicate that we are writing, aka programming a byte into the flash memory. And I need to create the write-byte function with its prototype in the header file. I'll create a param variable to scan in the value of the byte that we want to program. So I'll use scanf to get the value of the byte that we want to program. Make sure the function call was successful, and make sure the value is byte-sized. Else, I'll print out an error message. If we look at the datasheet, we can see the flowchart for the byte program algorithm in Figure 16. So let's load AA into address 5555. .55 into address 2AAA. And A0 into address 5555. Now we need to load the byte that we want to program into the current address. And now there's a few things that we could do here. We can wait for the period of TBP, use data polling, or use the toggle bit operation to determine the end of the program operation. For now, I'll just wait, and the value of TBP is 20 microseconds. So I'll wait for a full millisecond, which will be more than enough time. I'll print out OK to indicate that the byte has been programmed. Now, this should all work. But before we test it out, let's go ahead and use data polling to indicate the end of the program operation, so we don't waste a full millisecond, which is 50 times longer than the longest expected programming time. I'll create a low-level function named data polling, and we'll place the prototype in the header file. Let's look at the flowchart in Figure 17 to see how to perform data polling. So, after programming a byte, we read the most significant data bit, and if it is reading the correct value, then the programming period is complete. You know what? We don't need to look at just the most significant bit. We can check the entire byte, because if the most significant bit is off, then the byte won't be correct either. I'll set the address to the address of the byte we're looking at. And I'll create a variable to read the byte value into. Then I'll create a do-while loop and read the data into the poll variable. And we'll just keep looping as long as we read an incorrect byte. And of course, I need to enable the output before reading any bytes. Now I'll just replace the millisecond delay with the data polling function. And I want to post increment the address so the next byte gets written to the next address. And looking at the datasheet, we can see that the data polling should also work with the erase command. So I'll replace the 100 millisecond delay with data polling. And to finish this off, I'll go ahead and include the write byte command in the help printout. Beautiful. Let's test this out. There's all 8 of our commands listed. I'll ID the flash chip, read a byte to make sure it's erased, and set the address back to 0. I'll program a sequence of bytes from 0 to 3. Then check the current address. Make sure the next byte is erased, then set the address back to 0. Then read 0, 1, 2, 3, and FF. Remember that I said we could write a byte to a programmed location as long as we don't set any bits from 0 back to 1? I'll demonstrate that now. First, I'll set the address to location 10. I'll read that location to make sure it is erased. Then set the address back to 10. Now I'll write F7 to that address. We'll go back to location 10 and make sure F7 was properly programmed. Now let's go back to address 10 and try programming the value of F5. This will just set the second least significant bit from a 1 to a 0. Let's go back to address 10 and verify that it worked. And you can see that we successfully programmed F5 to a location that was previously programmed to F7 without first erasing it. And if I try writing 0 to that address, that works too. But if I try writing it back to F7, it just hangs. This is because the write byte command is using data polling to determine the end of the program period. And since we can't set bits from a 0 to a 1, the programming will never be successful. Therefore, the data polling will wait infinitely for the correctly programmed value. You could update this code to detect an infinite loop and print out an error message, but I'll just leave it as is since this is just a homemade programmer meant for hobby usage. Now that we've created a programmer that we can use to program a few bytes here and there, I have an assignment for you to complete, should you choose to accept this assignment. What I want you to do is to create your own command that will allow the Flash programmer to dump out a bunch of values read from the Flash chip. Here is an example of a dump command that I created. You use the letter D and follow it with a decimal number indicating how many bytes to read. So, for example, if I try dumping out 128 bytes, here's what I get. Notice the 0, 1, 2, 3, and 0 at location 10, which is the data we last programmed into this flash chip. I'll set the address back to 0 and dump out just 4 bytes. Then I'll dump out 16 bytes from address 0. And if I dump out 16 bytes again, it'll pick up from the address we left off on. Notice how I display up to 16 bytes per line beginning with the address, and I add a slight separation between two groups of 8 bytes. So that's your homework. Create a dump command and tailor it any way you'd like. In a future video, I will show you the code to my dump command. You might also want to make a command to query the size of the flash chip that was ID'd. There are all kinds of functionality you could add to this programmer, so have fun with it. Now, the only things remaining are to get this flash programmer to work with an app on a computer in order to send large files to it. And there are some modifications we'll need to make to this firmware to speed it up for sending large files to it. I'll cover that in one of the future parts of this video series. But for now, we can easily program just a few bytes here and there. So, we have the functionality we need for the next few videos I want to create, since in those videos I'll only be programming a few bytes. I will be creating a part 4, 5, etc., but those will come a little later. I hope you will enjoy the next few videos that I'll be creating and uploading, and we'll continue on with this project sometime in the hopefully not too far future. Thanks for watching, and I'll see you next time, right here on Dr. Plague.